Good morning students, welcome to video lecturing class. So the problem statement is an aeroplane with an autopilot in the longitudinal mode has a simplified open loop transfer function as g of s into h of s equal to k into s plus 1 divided by s into s minus 1 into s square plus 4s plus 16. For this, sketch the root locus and we find the range of a for the stability. So here the given values are in the standard format, that is g of s into h of s. So now you need to identify the number of poles and zeros. So here in the numerator we are having s plus 1, so there is 1 0, and in the denominator we are having three terms, s minus 1 and s square plus 4s plus 16. But for this you are having two roots, so therefore we can take the number of poles count as 2 here, 2, 3 and 4. So number of p is 4, number of z is 1. So their respective values are s equal to 0, s minus 1 equal to 0, so s will be 1. And if you identify the roots for this second order, we'll get it as minus 2 plus or minus 3.4 j, and the zeros are s plus 1 equal to 0, so s equal to z equal to minus 1. Now you have to compare the value of p, number of p and number of z. So p is greater than z, that is 4 is greater than 1. So number of branches required are 4. Then you need to identify the number of branches tending to infinity. So for that you have to take the difference between p and z. So p minus z equal to 3 here. So this is the number of branches ends at infinity. So you need to identify the angle of asymptote. So once the number of branches tending to infinity are 3, so the number of asymptotes required are also 3. So angle of asymptotes is given by theta equal to 2q plus 1 into 180 degree divided by p minus z. So q is 0, 1 and 2. Substitute those values, you will get the angles as theta 1 as 60 degree, theta 2 as 180 degree and theta 3 as 300 degree. Then you need to identify the centroid. So sigma equal to summation of real part of poles minus real part of zeros divided by p minus z. So poles are 0, 1 and it is a complex pole. So 0, 1, minus 2 minus summation of real part of 0. So the real part of 0 value is minus 1 here, and here this is minus 2, 2 times you have to take, and 1 and 0. Substituting those values in this equation, p minus z is 3, so your centroid is 0 minus 0.667. For that, need to identify the RL and NRL, and you need to mark the centroid. So first we will locate the zeros and poles. So there is only one zero whose value is 1 plus 1, so this is the 0, and poles are at 0, minus 1, and one is at minus 2 plus 3.46 j, and another is minus 2 minus 3.46 j. Now you consider a reference plane between 1 and 0. Toward this side the summation will be 1, so this portion is RL. Then consider a reference plane between 0 and minus 1. Here take the summation of p and z. So 0 and 1, that means it is an even number. So from 0 to minus 1 it is NRL. Then take the reference plane here and take the summation of p and z. So 1, 2 and 3. Okay, that means it is a RL part up to here. After that, if you take the reference plane somewhere here, so it is 1, 2, 3, 4, 5. That means after minus 1 it is a NRL. So here, sorry, RL. The NRL part is only between RL, this 0 and minus 1. Okay. Now according to the general prediction, you need to identify the breakaway point. One breakaway point should exist between 0 and plus 1, because this 0 and minus 1 is NRL. Remember, always breakaway point should lie on RL part. So one breakaway point will exist between 0 and 1. So to find the exact location, consider the characteristic equation 1 plus g of s into h of s, substitute that and simplify this equation to get the equation for k. So k equal to this one. Then differentiate this equation with respect to k. So it is u by v rule you have to apply here and equate that one to 0. Okay, so that is denominator as it is, differentiation of numerator minus numerator as it is, differentiation of denominator divided by this denominator square. So once you simplify this, you will get the equation as 3s raised to 4 plus 10s cube plus 21s square plus 24s minus 16 equal to 0. So now to identify the roots for this one by trial and error method, if you substitute s as 1, the left hand side will be 42, and if you substitute s as 0, that will be minus. So we are getting one value as positive and another value as negative. So one root lies between 0 and plus 1. So if you solve this equation for the roots, you will get one value as 0.445 is as the one of the root for this fourth order equation. Otherwise, by this standard deviation method, so this value will get it from the calculator, that is take s square as common, solve for second order equation, so that you will get one value as this 0.445. So now here write the coefficient of s terms. So 3, 10, 21, 24 and minus 16. So here as it is 3 will be there. So 3 into this term will be 1.335. Subtract that, add that one, you will get 11.335. Then this into this will come here, add this, you will get 26.044. Then this into this, substitute here, you will get this, add this into this, that is 35.59 and 0.445 will gives you the value as 16. So here it is with negative sign, so it will be 0. So now the equation is reduced to s minus 0.445 is one term into 3s square plus 11.335 s square plus 26.044s plus 35.59 equal to 0. So now it is a third order equation, so you can easily solve with calculator. So for that the roots will be minus 2.26 minus 0.75 plus or minus 2.16 j. So this s equal to 0.445 is a valid breakaway point because it lies between 0 and 1. Otherwise, if you substitute this s equal to 0.445, your k value will become 3.07. That is with the positive sign. And if you take this second term, the second root, that is s equal to minus 2.26, which lie on RL, so it is a valid breakaway point. Otherwise, you can substitute in the k equation, so that if we get there it is as a positive, we can take that one as the valid breakaway point. So here this complex root is minus 0.75 plus or minus 2.16 j. This real part is minus 0.75, which is left from the pole at 0. Cannot be a breakaway point because it is lying on NRL part. Similarly, if you substitute s as 2.26 in that k equation, you will get a k value as plus 70.56. So it is a valid breakaway point. So now to find the intersection of RL with imaginary axis, consider the roots array, that is s raised to 4 plus 3s cube plus 12s square plus 60 minus 16s plus as plus k equal to 0. First we need to simplify that characteristic equation. Construct this roots array. First s raised to 4 term, then s square term, then this constant. Similarly, s cube term, this s term, and here it is 0. Now to write the things here, 12 into 3 36 minus this into this k minus 16 divided by 3, and here to write this one k minus 16 into k 12 into 0 will be 0 divided by k minus 16. So k minus 16 in the numerator and denominator will get cancelled, left with only k. Similarly, construct this roots array. So here k cannot be 0. So I have to equate this term to 0. If you equate this term to 0, the entire row will become 0. Substituting that, we will get the k value as 51.2 and 16.76, because here you are having two terms, because it contains the numerator terms, that is zeros and poles. So that time you need to simplify that equation to get the value of k. So here you will get that equation as the second order equation. So solve that equation to get the roots of that particular second order. So we'll get two roots as 51.2 and 16.76. Now consider the auxiliary equation, that is the row associated with s square. So this into s square plus k equal to 0. So if you substitute k as 51.2, s is plus or minus 13.87 j. Now substitute k as 16.76, you will get plus or minus 1.2 j. That means your root locus will cut the imaginary axis twice, once at 13.87 and second time it will cut the imaginary axis at 1.2 j. Now there is a complex pole. You need to identify the angle of departure. For that, first you mark the poles and zeros. Take this one as the reference pole. To this pole, join all the poles P and Z with a straight line. Okay. Now pi P1 will be 180 degree minus tan inverse of 3.46 divided by 3. Because opposite is height is 3.46 and here it is 3. From here to here it is 1, 2 and 3, because this is put together from 0 to minus 2 is there, and here it is starting from 1 here, and opposite side is the height of with the imaginary axis is 3.46. that value you have to substitute here. So it is 131 degree. Similarly, pi P2 will be 180 degree minus height will be same, opposite will be same, 3.46 divided by 2, because here starting at 0. And then pi Z1 is 180 degree minus tan inverse of 3.46 divided by 1, this angle. And pi P3 is vertical line to this pole, so it is 90 degree plus 90 degree. Now pi value is summation of pi P minus summation of pi Z. So if you substitute those values, you will get pi as 235 degree, and pi D is 180 degree minus pi. Pi is 235 here. So here you will get the value as 54.88 degree as the angle of departure. So pi D for a pole minus 2 minus 3.46 j is plus 54.88, and for another it is minus 54.88. Now to construct the root locus, first you draw the S plane, that is real axis and imaginary axis. Mark the poles and zeros. One pole is at 1, 0 and minus 2 plus 3.46 j, and minus 2 minus 3.46 j, and 1 0 is there whose value is minus 1. After that you have to mark the centroid. Centroid is here. From there you need to mark the angles for the asymptotes: 60 degree, 180 degree and 300 degree. After that need to mark the intersection of the roots with the imaginary axis. One is at 1.2 j, another is at 13.07. Then for these complex poles you need to mark the angle of asymptotes, angle of departure. So for this pole it is minus 54.88, draw that line, and for this pole it is plus 54.88, draw that line. Now we need to draw the roots. The first one will start from the first pole whose value is 1, that is from here it will start and it will come to the breakaway point. From there it will divert with the angle 90°. Then it will have the intersection with imaginary axis at 1.2j. Then again it will have the intersection with imaginary axis at 13.87. Then it will tend to infinity by following this asymptote. So this asymptote line and the tending line of this route will be parallel to each other. So starting from 1, coming to the breakaway point, having the intersection with imaginary axis at 1.2j, then second time it is having the intersection with imaginary axis at 13.87j, then it is tending to infinity. After that, the second route will start from 0, because always starting points are going to be poles, ending points are going to be zeros. So it is starting from 0, it will reach to the breakaway point, then it will leave that path. It will have the intersection with imaginary axis at minus 1.2j once, and the second time it will have the intersection with imaginary axis at minus 13.87j. Then it will tend to infinity by following this asymptote. The third route will start from this point, minus 2 plus of 3.46j, and it leaves tangentially to minus 54.88, and it will reach to the breakaway point at 2.26. Then it will end to this point, because the ending point for this route is a 0, whose value is minus 1. Similarly, this route will start from minus 2 minus 3.46j, and it will leaves this path tangentially to the angle 54.88. It will reaches to the breakaway point, which is at minus 2.26. Then it will tend to infinity. So these are the 4 routes. Then the last, you need to comment on its stability. If k is greater than 0 and if it is less than 16.76, some routes are on the right half of the S plane, so system is unstable. If k is 16.76, system is stable. If the k value is between 16.76 and 51.2, system is stable. If k is greater than 51.2, unstable. If it is exactly equal to 51.2, is marginally stable. So this last step is also to write. So if you have any doubt, you can leave the comment in the comment box. Thank you.